Assalamualaikum and hi guys. So today I would like to share about hydrostatic force on curved surface. So as we have discussed in the previous lecture, for hydrostatic force on submerged surfaces, we have two types of surfaces. One is plane. Okay, this is an example of plane. Okay, the retaining wall, the aquarium. Okay, and another one is the curved surface, like this one, tank with a curved surface. Okay, and in one of my videos, I have also explained on the derivation of hydrostatic force equation and also its location. Okay, so this is the hydrostatic force equation. However, this equation is applied on a plane surface. Okay, where FH is the hydrostatic force, or also can be written as FR, equals to rho GH bar A or gamma H bar A, and H bar can also be written as HC. So H bar is the vertical height that is taken from the water surface to the centroid of the plane surface. Okay, this plane surface can be of any shape, any arbitrary shape, for example, rectangle, circle, and etc. Okay, so this is the equation for the location of the hydrostatic force. It is located slightly lower than the centroid of the plane surface, okay, through the CP, okay, center of pressure. Okay. So, how are we going to apply those the equation and also the location of the force on a curved surface, because it is non-planar, okay, non-planar, not a plane surface, it's a curved surface. So if you can see here, this white color is the plane surface, and the red color is the point at which the resultant hydrostatic force acts. Okay, so the force is acting on point, red point here, okay, red color. And if you can see here, this force, if you resolve, okay, if you resolve the force to x and y direction, you should get fx and fy like this. Okay, this F is the resultant hydrostatic force. This Fx is the if you resolve this force to x and y, you will get Fx and Fy. Fx is the horizontal force, Fy is the vertical force. So what is Fx and Fy and how to determine? Okay, you can actually use the same equations for planar surface to find Fx and Fy. So I will show you the steps. Let me show you. This is an example of a curved surface. So if you can see here, we have A, B, and C. So B to C is the curved surface. Alright. Okay. So the resultant hydrostatic force can be located somewhere here. Okay. Fr. Okay. So if you resolve this force, okay, to x and y, you get Fx and Fy. But before that, the first step that you need to do is to isolate the volume of fluid bounded by the curved surface. So how do you isolate? You take this curved surface, okay, so from here to A, okay, there's another point here, A is the water, okay, and from A to B is water. So you have a closed loop here. So you isolate this volume, okay, and you redraw. So I will redraw. Okay, like this. So this is C, this is B, this is A. You isolate the volume of fluid bounded by the curved surface. Alright. So the second step, the second step is to draw the free body diagram. So as I've mentioned, this FR, if you resolve, you will get the FR. If you resolve, you will get summation of horizontal force, okay, and summation of vertical force. So in this volume, okay, you should have Fx, okay, that comes from the force, okay, Fh, horizontal force, that is acting on the imaginary surface, vertical imaginary surface. So why I say it's an imaginary surface, okay, it's because the surface actually doesn't exist. Okay, it's just water, but for you to um, to determine the hydrostatic force, you must assume that there is a plane surface here. Okay, all right. So this is the depth or the width, okay, or the width, and this is the height, okay, the height of the imaginary surface. Okay, is the water surface, okay, at which the force acts. Okay, and in this case, this h is the radius of the curve. Okay, the radius. Okay, so so to determine this, you can use the equation for the hydrostatic force on plane surface, where Fh is equal to rho g or gamma h bar A, okay, where h bar is the vertical height that is taken from the water surface to the centroid of this imaginary surface or imaginary area. Okay, so in this case, from here to here, okay, they say the imaginary surface centroid is here. Okay, here, all right, between A and C, halfway. Okay, so from the water surface to this point, it should be the H bar. Okay, the H bar. So I call it as H bar horizontal. So H bar horizontal. While the FH should be slightly lower than this centroid. Okay. So if you want to see, you draw here. If you want to draw here, it's somewhere here lah. So the CP should be somewhere at this point. Okay, at the line, at the point where the force act. Okay, so basically it's here lah, CP. Alright, and this area should be the imaginary area that I mentioned just now, which is the area at which the imaginary area or the water surface area, okay, where the force act. Okay, so in this case, since the force is horizontal, so the area should be vertical, perpendicular. Alright. So it's rectangular shape, height times width, okay, or radius times the depth. Okay, and that is second. Draw the free body diagram. There's another force here. Okay, since there's water above this curve, okay, it's not open to the atmosphere. There's water above, so there will be another force acting at the top, okay, somewhere here. And since it doesn't have any change in the elevation here, it's the same height here, so it is acting at the centroid because pressure is distributed equally. So at the centroid. Okay. And to find FV, similar, gamma H bar A, where H bar is the vertical distance that is taken from the water surface to the line of action of the force, a centroid here. So in this case, I use different color here, blue. It's this distance. It's a straight line actually, H bar B. Okay. And area is the imaginary area at which the force acts. In this case, if you draw it in 3D, you get this. Okay, so the imaginary area is radius, height, times with width or depth. Okay, similar to the vertical imaginary area. Since the force here is vertical, so the area is horizontal, perpendicular. Okay, and don't forget that inside this volume, you have weight. So weight of water inside this volume. Okay, so weight can be determined by using specific weight times volume. So in this case, for this particular diagram, the area, the volume of the fluid enclosed by the curved surface is of what shape is this? This is a quarter cylinder. Okay, a cylinder. Alright, you have a quarter. Okay, this part only. Okay, this part only. So a quarter cylinder. So pi r square L you divide by 4. Okay, so r is the radius. Okay, maybe I should use the same notation here. L also, L is the width. So I use W, okay, or depth here. So it's divided by 4 because a quarter. Okay, but for different diagram, maybe the curved surface can be of hemisphere, okay, like a dome shape. So you have to change the volume equation or formula. Alright, so it can be like this. Okay, it can also be like an inverted curve, okay, where the water is here. Okay, alright, so it depends on the shape, the location or the shape of the curved surface. Alright, so that's it. Oh, not yet. Okay, before that, that is for FH and FV. So how do you get FR? So basically, if you can see here, the weight, where is the weight? The weight is acting through the centroid of this what we call that, quarter cylinder. Okay, so weight is here, going down. So weight is going down. Okay, so if you draw here, let's say the quarter cylinder centroid is here. The weight is going down. The distance here, the distance, if it's a quarter cylinder, quarter circle, this one you can actually get from the diagram that I've provided for the formula of common shape. Okay, this is 4r over 3 pi. This one also 4r over 3 pi. Okay, this is the location of the centroid of the quarter cylinder, quarter circle. So the weight is acting downwards. So if you can see here, the summation of force in x direction, we only have FH. the summation of force in y direction, we have in this case Fv and weight that is going down, so Fv plus weight. Okay, so this one depends on like I mentioned just now, if it's sometimes you can also have Fv minus W because Fv is going up. Okay, but in this case Fv is going down, so Fv plus weight. So if you want to find the resultant force, so Fr is Fx squared plus Fy squared, then square root. Okay, so that is the magnitude of Fr in Newton force. Okay, alright, so that's it for the magnitude. In the next video I will explain, or maybe in the online class I will explain on how do you find the location of Fr. Alright, so see you then. Thank you.